Welcome to lecture 13. We have been studying the principal stresses and the mode circle, how the stress vary within the soil with different directions and how to find out those. Today, let us look at how different aspects of civil engineering cause stresses in the ground and how they vary with depth. So I would like to talk about stresses due to firstly, gravity, which we have already discussed. Second, I would like to look at the stresses due to structures. We build on them very briefly because you would study more about them in the course on foundation engineering. Third, we'll talk about stresses due to flow. We call them as seepage stresses. And this leads to a very interesting phenomenon of piping, which is a very serious problem in geotechnical engineering. And lastly, we have what is called as capillarity. That is the effect of water above the groundwater level. It's a very interesting engineering physical phenomena which has a lot of implications in civil engineering. Now let us take one after the other. First, what are the stresses due to gravity? Let us say we have ground level here and the groundwater level is somewhere here at some depth. Let's say this is some depth of water table which could be 2, 4, 6 meters, etc. The soil below the groundwater level would be saturated because all the soil is below water table. So let us say I call it gamma S. Above the water table, the unit weight can be less or equal to gamma saturated. So when I want to calculate stresses due to gravity, you know that the gravity pulls everything downward. Let us say if I take a point at a depth z within the zone above the water table, you can simply say sigma z is equal to gamma total into z, where z is the depth to the point. Let's say I call this point A. But if the point B is below the water table and the depth is z, now we'll have to calculate what will be the total stress, and the point is below the groundwater, so it will have pore pressure also. And then we can calculate effective stresses. We have already defined the concept of effective stress. So if I want to find out up to a depth dW, the unit weight of the soil is gamma total, and below the groundwater table, the unit weight is equal to gamma saturated. So we calculate the total stress is equal to gamma total into depth to water table, and the net depth from the groundwater table would be Z minus dW. So this should be equal to plus gamma saturated into Z minus dW. All we are doing is calculating weight of the soil per unit area with respect to the depth of the point. And the point here is below the water table, and the unit weights are different above and below the water table. Above the water table, it is gamma total, which may be equal or less than gamma saturated, but below the water table, all the soils are saturated, so we should take the saturated unit weight. So this will be our total stress at the point B. What will be the pore pressure at the point B? You can see that water level is at depth dW from the surface. So with respect to the point B, the height of water level is Z minus dW. So pore pressure will be equal to unit weight of water into Z minus dW. That's how we calculate the pore pressure at point B, because water table is at a height of Z minus dW. So pore pressure is straight away equal to unit weight times the depth or elevation of the water table. So now we can call effective stress at point B is equal to, shall I say this point B, the total stress at B minus pore pressure at B. So this we call as pore pressure, which is very simple to write, which is equal to subtracting those two, gamma T into dW plus gamma S into Z minus dW minus gamma W. UB is equal to gamma W into Z minus dW. You can see that Z minus dW is common, so we can subtract gamma W from gamma S, and if you do that from the saturated unit weight, if you subtract the unit weight of water, we get back our submerged unit weight. So we write it as gamma submerged or gamma boils into Z minus dW. So this should be the vertical effective stress at point B. And as you can see, as you increase depth Z, all the stresses increase, and the rate at which they increase depends, of course, on the unit weight. Above the water table, the rate of increase is equal to the total unit weight. Below the water table, the total stress increases at the rate of saturated unit weight, whereas the effective stress increases at the rate of gamma submerged. I would also like to introduce to you a new term called the K0, which is the coefficient of earth pressure at rest. It's a new term you probably would be using a lot. It defines actually the ratio of K0 is equal to sigma dash H by sigma dash Z. What is that? The ratio of effective horizontal stress by the effective vertical stress. So this is effective horizontal stress divided by effective vertical stress. So if you know this property of the soil, which is a function of its whether strength or elastic properties, you can calculate what will be the horizontal stress. So that when I have an element here, now that you know sigma dash Z, you can calculate sigma dash H. Please remember, K0 defines the ratio of the two effective stresses, effective horizontal stress divided by effective vertical stress. K0 usually varies from around 0.25 to about maximum 0.5. Now that tells you the relation between the vertical stress and the horizontal stress. If I know the value of K0, then I can calculate sigma H, effective stress. That would be sigma H prime is equal to K0 times sigma Z prime. You know how to calculate sigma Z prime from this expression. If I multiply the effective vertical stress, we get the effective horizontal stress. Then the total horizontal stress is equal to effective horizontal stress plus U at the point B, of course, wherever you are measuring. The reason is water pressure is hydrostatic. It is the same in all directions. So what finally you can say is that at a point in the ground, particularly below water table, we'll have these stresses. If I take a small element, this I am enlarging at point B, we'll have sigma Z, this will be sigma H, and we'll have U, pore pressure. And these are the total stresses and pore pressures. And if I want the effective stresses, we'll have to write it as sigma Z prime, sigma H prime, so basically what you are saying is maybe I can separate out this pore pressure then you will appreciate it better, minus, so I'll put it here, this is pore pressure. So you can see that sigma total stress minus pore pressure is equal to effective vertical stress. Total horizontal stress minus pore pressure is equal to effective horizontal stress. So we can now calculate at each point these stresses. P is equal to sigma z plus sigma h by 2. This will be the effective average stress. P prime is equal to sigma z prime plus sigma h prime by 2. This is the center of the Mohr circle we talked last time. Q, half the difference would be sigma z minus sigma h by 2, which is also equal to sigma z prime minus sigma h prime by 2. The reason is, you can see that the difference between the two principal stresses will be exactly the same because you are subtracting the parameter, the pore pressure u. So the radius of the circles will be exactly the same. So if you are now plotting the Mohr circles, we will have, this will be the total stress circle, whereas this will be the effective stress circle. And what will be the distance between these two? Is equal to the pore pressure, which will be the same here. So if you want the center, this will give me P, this will give me P prime, and the radius R will be exactly the same because the Mohr circle got shifted. So when you want to visualize the state of stress within the ground, you will find that, for example, the total stress will increase this way, the pore pressure will increase. I'm plotting with C, and then you can see that this is total, this will be effective, and this will be pore pressure. You agree that pore pressure starts from groundwater level and it's increasing linearly. I just didn't take the account of the difference between total stress, unit weight, saturated and total. So I'm taking a single line. And the difference between these two will give me the increase of effective stress with depth. So this is 0, point A, B will be here. So the slope here, the gradient, is proportional to the unit weight, total unit weight, and the slope here below the water table will be submerged unit weight. This gives you a picture. If you want to combine this with horizontal stress, all that you have to do is multiply the effective vertical stress with K0, you will get the horizontal stress. So that way now the complete picture of state of stress within the ground due to gravity will become very clear. Once again, you calculate the vertical stress using unit weights, subtract the pore water pressure to get the effective vertical stress, multiply effective vertical stress with K0. I'll tell you later in one of the lectures, that this is approximately equal to what we call as 1 minus sine angle of shearing resistance. So we know how to estimate K0. We'll have standard tables from which we can find out. And using that, you will get effective horizontal stress. From there, you will get total horizontal stress. And once we know all of them, you can plot the Mohr circles, and you can also get the stress points, which are nothing but the coordinates based on P or P prime and Q. This is P and Q, these are the coordinates. This is P prime and Q. So we know how the stress points lie on the new stress space of P and Q. These are the stresses due to gravity. Now let us look at how stresses vary due to structures. suppose we are building due to structures, which we as civil engineers build on the ground or inside the ground. So I have a building here. So I can say that the weight is acting, and usually of course we have depth of the foundation at some depth here. Or you can have, here is the ground level, you are building an embankment so that you can have a highway or a railway on top of it. So this is an embankment. And what will be the weight? It's equal to the weight of the soil. So if the embankment height is h, we say the stress Q is equal to gamma embankment into h, which is again simple gravity stress acting on top. You also would see as you go along, there are a lot of these liquid storage tanks, Indian Oil, Bharat Petroleum, etc., and they have all the petroleum products inside, which will be equal to gamma fluid into height of the fluid inside. So what you find is stresses are acting on the ground or inside the ground. This is not at the surface. For most buildings, the foundation should be at some depth. Why? Because the soil near the top is not reliable. Secondly, during rain, it may get eroded. So we say DF should be generally according to code greater than about 1 meter, greater than or equal to 1 meter. For very big, tall structures, heavy structures, we take them down below. For normal houses, 2-3 storied, you may have DF is equal to 1 to 3 meters, etc. But for the sake of simplicity, I would like to start with a very, very simple solution, which was given by Boussinesq in 18. He's a French mechanics expert, I think somewhere around 1885, about 125 years ago. He looked at a point load. That is what you call in mechanics as a concentrated load, which is the easiest solution one can derive. What he found out was simple analysis. At any depth z and at a radial distance r, suppose I have a point A. The load is applied on the surface. Please remember, this is the surface of the ground. And if you apply a concentrated force P, what will be the stresses? What will be the various stresses? In particular, we would like to know what is the increase in vertical stress. He gave a very simple solution for the vertical stress, which is equal to 3 times P 2 pi z square into some influence coefficient, IF. IF is again a very simple expression, 1 by 1 plus what is the increment in vertical stress due to the applied load P. Please remember, P is a force, Z is the depth at which you are interested, and R is the radial distance from the vertical force, and this is what you can call an axisymmetric problem. If I have vertical force downward, it doesn't matter whether the point is towards you, to the right, to the left, or behind. All that matters is what is the radial distance from the axis through the force P. So this is called an axisymmetric problem. The two variables are the depth and the radial distance from the axis through the force P. Since, as I said, P is a force and Z is a length measure. It can be 2 meters, 5 meters, 10 meters. So it's a length measure. So you can see P by Z square will give me the stress. And if you look at the influence coefficient, we have a ratio R by Z. R is again a distance and you are dividing by the depth. So it becomes a dimensionless term. So this is influence coefficient which is non-dimensional. What you can notice very interestingly is sigma z, the increment in vertical stress due to structure. This could be the weight of the building, weight of the embankment, or the weight of the tank, whatever it is you are considering. You will find that the force divided by stress, which is square of the distance, which is z square, into some influence coefficient. As z increases, it is to the power of depth. Can we say that stresses decrease very rapidly with depth? Which is true, because P by z square will be decreasing very fast. Similarly, if R increases, they also decrease. So basically what we realize is that if I plot here sigma z versus depth, you will find that stresses decrease very fast. Theoretically, near the surface where z is equal to 0, they tend to infinity, and then as depth increases, the stress will decrease. The second interesting thing would be how are they distributed in the radial direction. If I take a plane close to the surface, the stresses are concentrated under the load. As you go deeper, let's say this is 2 meters, now I am looking at 5 meter depth, you will find that the stresses are getting more uniform. The maximum value will decrease and the load will spread laterally. So basically what you are saying is approximately it is decreasing with distance, with depth, and it's getting spread over a larger area. Before we got this analytical solution, people were taking it as 2:1 distribution. So if I go a depth of 2, or the variation would be 2 vertical and 1 horizontal. This is called 2:1 variation. So if you are going 2 meters, the load is spread 1 meter farther apart. So that's how we calculate the distribution. But we don't need to go for that simple one. What we normally do is calculate this for a point load. Why I'm presenting this is because the solution is very easy. But now that you know these expressions, you can easily integrate for any other type of load. Can you imagine a railway where you have a rail going long miles and miles? So I have here, this is the line load, we call it. If you are applying, all that I had to do is integrate along this distance. This is x, this is z, and this is, say, direction y. So we have a line load. We also, next extension would be a strip load. The ballast will distribute the load over a finite width. So when I'm looking at a load over a finite width distributed, this extends to infinity. You can look at a simple compound wall in your house or adjacent to it. It runs, say, let's say 5-10 meters, and the load of the wall is distributed through the footing over a finite width. This is called a strip load. And finally, we come to a uniform circular load where you have average stress Q, and we know how to integrate this simple point load to various cases, and you will use them when you are doing a course on foundation engineering. We sometimes call geotechnical engineering 2, where you would like to know what kind of stresses are transmitted to the soil below the ground due to whatever structure we are building on top. I will not go into this except to say anything you build on the ground or within the ground will increase the stresses at various points, and you need to find out the increase in stress over the gravitational stress. the third one, I'm sorry, is the stresses due to flow. It's very interesting. When a flow takes place through the soil, the water is losing the head, which means it is losing its potential. So where does it go? In probably fluid mechanics, you would call it as a drag force, and similar to that, the same drag force is transferred to the soil particles, and so we get what is called as seepage force. Just to give you a simple illustration, let's look at a permeability test where you have a soil of length L, and this is the upstream water level. At the bottom, I am connecting another reservoir and maintaining the water level here. So you can see the net difference between these two is the H head, and you agree that this head is going to cause flow in the vertical direction. This is the downstream water level. This is the bottom of the soil sample. This is the soil here, and the reservoir on the downstream side is connected to the bottom, so that if I put a piezometer here, what will be the level up to which water will rise? Up to here. And what will be the level up to which water will rise in the point, let's say I call it as point A, point B. And if you take any other point C and you put a piezometer, obviously it will be somewhere here. So this difference between upstream and downstream is H, which is the net head loss. Let us plot the total and effective stresses, pore pressures, etc., to see what is happening to these stresses. Suppose I want to plot with respect to this point. I take this as a datum. This is the depth. How does the total stress increase? From here to this point, the unit weight is water. I have saturated unit weight. So can I say up to here, it is gamma W into whatever depth. Let's say this will be equal to some L1. And from here, let's not go too far below, we'll stop somewhere here. This will be equal to gamma W into L1, whereas at the bottom, the total stress sigma Z is equal to gamma W into L1 plus gamma saturated into L. So the total weight acting at point A, total vertical stress, is equal to weight of water plus the weight of saturated soil. How does the pore pressure vary? Suppose I plot now U versus depth. I have taken the datum here, so there is no pore pressure here, and pore pressure here again is increasing. But what will be the pressure here is equal to L plus L1 plus H, the net head loss. So you will find that this is equal to gamma W into L1, whereas this pore pressure at point A will be equal to gamma W into H plus L1 plus L. The pore pressure here is connected to the upstream reservoir, which is at a height above the downstream one. So the water pressure here would be equal to whatever is the corresponding level of the water here? H plus L1 plus L. Now can I calculate the effective stress so that I can plot? Please remember these two are equal, so the effective stress will be 0 up to a depth of L1, and it will be difference of these two. Total stress, this is equal to sigma z, and this is for pressure. So I can say, what will be this value at a depth equal to, this depth we said is L, sigma z prime at point A will be equal to the difference between these two, gamma W L1 plus gamma saturated L minus gamma W L1 minus gamma W into H plus L. Try to simplify this, gamma W into L1, and you have gamma saturated into L, gamma W into L. If I subtract, this will be equal to gamma submerged into L minus H into gamma W. Can I write it as equal to gamma submerged into L minus H by L into L into gamma W? I'm sorry, gamma submerged. What is H by L? It's nothing but the gradient. You have defined earlier in permeability studies, the gradient is equal to head loss divided by the length. So you now find that gamma submerged minus I gamma W into L is equal to 0. Suppose we keep on increasing the height H. What happens? If I increase height H, H by L increases and this gradient I increases. Is it possible at some stage, hey, gamma submerged is equal to I gamma W? That is called the critical hydraulic gradient, which is obtained as when sigma dash is equal to 0, which means gamma submerged minus I gamma W is equal to 0, and that gives us I critical is equal to gamma submerged by gamma W. If you remember, we said gamma submerged is G gamma W into G minus M, sorry, by 1 plus C, and I have gamma W. So we get critical hydraulic gradient is equal to G minus 1 by 1 plus C. It is usually in the range of 0.9 to 1.1, and if the upward gradient is of the order of around 1, the soil will start getting lifted, and this phenomenon is called piping, or you can say soil starts boiling. It looks as though when you see water being boiled in a container, you get all the bubbles coming up. Similar to that, you will find all the soil coming up in the bubble form. What is the significance of this? Suppose I have the groundwater level here. I want to build a swimming pool. I make an excavation and I provide a sheet pile or a barrier. The water will try to come up into the excavation. You can see that the water is trying to come up as flow. This is a sheet pile. So it doesn't allow any water flow in this direction from the sides. But the water can go down and come up below the excavation, and then you will find that if you are not careful, you will have a lot of piping depending on the depth of excavation. A similar phenomenon occurs. Suppose you build an embankment or an earth dam, and you have stored water here. This may be impervious, but the water can flow below the embankment and you will find piping occurring. If you don't provide, sometimes you will find erosion also, but that is a slightly different problem. But the point I would like you to see here is gamma submerged is unit weight due to gravity minus of course the buoyancy. I gamma W is again a force unit because you are multiplying by unit weight of water times the gradient. So this I gamma W is called the seepage force, where of course unit area if you do that. So if I have gravity acting downward, this will be the weight gamma saturated. If the flow is upward, you get I gamma W. So this creates an upward force for flow upward. Suppose I have downward flow. Here I am flowing. You find that this will be downward I gamma W, but as long as the seepage force is downward, it does not cause any problem in civil engineering. The problem is only due to upward flow. There are many instances where this could be a serious problem if you are not careful. One more last thing I would like to add here is the fourth type, which we call as a capillary rise and capillary force. We call it capillarity. Suppose you take a tray of water in a container. Let us say you put a big diameter tube, a medium diameter tube, and a capillary tube. So let me call it D1, D2, and D3. D1 is greater than D2, greater than D3. What will be the water level in the three tubes? This is any fluid. It can be water or any other liquid you want to put in. You will see that in the larger tube, the water will rise only at a small amount, whereas in the intermediate diameter tube, it will rise higher. And if you look at the capillary tube, the height of capillary rise is very high. What the physicists tell us is that this capillary rise is equal to 40 cos alpha by gamma fluid into diameter. And please note that this meniscus, this is called the meniscus, is not horizontal, but it's curved. And if you look at this, this angle is alpha. The angle the fluid makes with the vertical face of the tube is called alpha. And from physics, you know the capillary rise is equal to Hc 4 times the tension in the fluid tension into cos alpha divided by unit weight into d. Now we can say that alpha is equal to 0 for water and with respect to glass, which is same as silica. So I'll replace Hc is equal to 4T by gamma W. T is called the surface tension. Now this is with a tube. In the soil, we don't have a tube, but what we have is the void space. You have all these particles. So the diameter or the size of the void matters. In case of sands, the void space is large. In case of silts, it's intermediate. And in case of clays, D is very, very small. This D, the size of the void within the soil, is approximately equal to D10, the particle size corresponding to 10% finer. It can vary from, let's say, 0.1 millimeter to as low as 0.01 millimeter. And that gives rise to enormous increase in capillary rise in case of silts and clays. In case of sands, HC can be of the order of only 0.1 to 0.2 meters. Coarse sand, fine sand may be around 0.3 to 0.5. In case of silt and clay, it can vary from 0.5 to maybe even 3 meters. You find that the water rises very high in the clays. So above the water table, you will find some water. So now let's look at capillary rise in the soils. Here is the ground level and here is the groundwater level. You will find that if I plot, let's say, degree of saturation, obviously it's 100% here, and if I look at it, it will be something like this. Please remember, this is equal to the capillary rise. The capillary rise can be 0.5 meters, 1, 2 meters, depending on the soil. So that's how it varies. This is 100%, and this will be very small, what you can call hygroscopic moisture, 6 to 8%. So water can rise, but this will be under negative pressure. We'll discuss this at a later stage, and we'll talk more about it when appropriate.